air enters a 1 inlet, 1 exit control volume. It's got a pressure of 6 bar, 500 Kelvin, and a velocity of 30 meters per second. It's got a flow area of 28 centimeters squared. Now, those were the inlet conditions. At the exit, the pressure is going to be decreased to 3 bar. The temperature has decreased to 456.5 kelvins. The velocity has increased to 300 meters per second. Air is going to behave as an ideal gas. And then we're going to have steady state operation. We need to find flow rate, mass flow rate, and the exit flow area. So if we draw a picture of this, let's say it looks something like that. This will be our inlet, this is our exit. So here we've got 6 bar, our temperature is 500 Kelvin. We've got a speed of 30 meters per second. And then this area, called AI, is 28 centimeters squared. At the exit, our pressure is now 3 bar. Temperature is 456.5 Kelvin, and now velocity has really increased to 300. Before we start, notice the keywords. We got ideal gas, steady state. First we want to find mass flow rate. Remember that equation is rho AV, where V is velocity. Now, if you notice here, we don't have anything about density. We've got the area, we've got the velocity, we don't have density. So, we need to do something else. Notice it also says it's an ideal gas. So that gives us another equation that has density in it. That one is pressure equals rho RT. Now, if we can solve this one for rho, which is pressure over R times T, then we can take this, plug it in over here. I know we're kind of going backwards here, but that'll give us m dot equal to pressure times area times volume over RT. Okay. Now that we have this, we've got all of these values. We can find R, that just comes from the table. So all we need to do now at this point will be plug in our values. Pressure is 6 bar. And the area is going to be 28 centimeters squared. Let's convert from centimeters. We don't want to leave that in there. So cube or meters squared is equivalent to 100 centimeters. Let's square that. Then our velocity is 30, so let's multiply that by 30 meters per second. Then the denominator is going to be R times T. Our bar is going to be 8,314. That's Newton meters kilomole Kelvin. Put that over molecular weight. That's 2897 kilograms per kilomole. Whoops. And then multiply by temperature. Temperature is 500 Kelvin. Now let's look at the units. Kilomoles gone. Kelvins gone. We've got centimeters. That's gone. Now if you look here, we've got a couple more things here. We've got meters. That goes away. Now we're left with all of this other stuff that we've got. Okay. So let's go ahead and do the conversion. We need 10 to the 5th Newton per square meter per bar. That will take care of the bar part, which we want to get rid of. And then it'll also help us get rid of newtons and the square meters, leaving us with, it's hard to see it, kilograms per second. Okay, so after you do all that, multiply all the numbers out, you're going to get 0.351 kilograms per second. Now, an important thing you need to note here is that it just said find the mass flow rate. It didn't specify at the inlet or at the exit. And can you all think of why that is? Remember, This is steady state. So steady state helps us with our mass flow equations. So at the inlet, it's the same thing as at the exit. So really there's only one m dot term. All right, so both of these locations, mass flow rate is the same. Right, so you have 0.351 kilograms of air traveling through your inlet and your exit per second. Now for the second part, we want to find the exit area. So we want to find that right there. All right, and we can call it AE. We need to find that. So let's use this same equation here, but let's use the conditions at point 2 or at the exit. For this, I just used the conditions at 1 or at the inlet because we had that area available. We couldn't use the exit conditions because I didn't have enough information. So now let's just go to the exit conditions. Oops. So we'll have our pressure at the exit times the area at the exit times the velocity. Put that over R times the temperature at the exit. Pressure is 3 bar. Let's get rid of the bar. So we'll have 10 to the 5th Newton per square meter per bar. Multiply by the area. Multiply by the velocity, 300 meters per second. Divide that by R. So you'll have R bar over M, like that. And then you got all your units up here. Same thing we had before. So you're left with that, and then your temperature at the exit. Temperature at the exit was 456.5. That's Kelvin. Now, your only unknown here is A2. We can solve that because we already know what ME dot is. That's the 0.351, right? So let's set it equal to 0.351. And now we can solve. And if you do that, you'll get your exit area. And this is messy, guys. Sorry about that. So your exit area then is going to be 5.11 times 10 to the negative 4 meters squared. And of course, it wants centimeters squared after I just boxed that up. So if you convert it over, it's 5.11 centimeters squared. So that'll be your exit area. So we decreased that exit area, and in doing so, we've also changed our properties there. All right, hopefully that helped you out.